Why, hello. Today we're going to go on to section 17.6, which deals with parametric surfaces and their areas. Now, you might recall previously we learned how to represent curves parametrically. Like here's an example where we have a three-dimensional curve in space that we wrote as x equals 2 cosine t, y equals 2 sine t, z equals t, and t was called the parameter. And as we let t be various values, we would get certain points, x, y, and z, and as we plotted those points, the curve would be defined in three-dimensional space. Today, what we want to do is we want to represent a surface parametrically. Now, the thing to remember is, on a curve, this particular curve, if you notice, if you go x squared plus y squared, you'd get 4 cosine squared plus 4 sine squared. And since cosine squared plus sine squared is equal to 1, this would equal 4. So this particular curve is on the cylinder x squared plus y squared equals 4. But what's happening is, as t's increasing, you might remember you would be doing something like this, going up further and further as you're wrapping around that cylinder. But notice, a curve is one-dimensional. As I go on the curve, there's just two ways I can go, forward or backward. I can move along the curve. Only one way to go. So we call it a one-dimensional shape, one-dimensional figure in space. Now with a curve in general, a surface in general, if you think about it, if like this is your surface, and if I'm at a point right here, I could say, well, I could go this way, or maybe I could go this way. And if I wanted to go obliquely, I could write this spot obliquely as a combination of these two vectors. You know, stretch this one so much, and then stretch that one so much to get there. So a surface is two-dimensional. If you think about it, a surface is two-dimensional, and therefore, if you're going to represent a surface parametrically, you'll probably have, or you will have, two parameters because it's a two-dimensional figure. You with me? Where a curve is one-dimensional. You're just moving along this one linear, like along this line. Well, this is very much like a plane. So how can I represent the surface x squared plus y squared equals 9 parametrically? Well, if I looked at this as just in two-dimensional space, okay, since we have x squared plus y squared equals 9, since I know cosine squared plus sine squared is equal to 1, if I let x equal 3 cosine t and y equal 3 sine t, then I would have x squared plus y squared equal to 9 cosine squared plus 9 sine squared, and I could factor out the 9, and get 9 times 1, which is 9. Now you go, well, this is a surface, Mrs. Strocko. X squared plus y squared equals 9. Yeah, down here it's a circle in the xy plane, but z can be anything, so you can go up or you could go down, right? Perpendicular to the xy plane and get more points. So we're going to let z be z. Okay, so we're sort of like representing the points on the circle parametrically, and then we're letting z equal to z. And notice, what are my parameters? My parameters here are t and z. And notice, if you let t range from 0 to 2 pi, you'll get any point along the circle here, and then let z, you'll go up and you'll get your point on the curve. So here I've taken something that's an xy form and I've represented it parametrically. And notice we have two parameters. Suppose, now I want to show you that yeah, question.
Yeah, for page 2 you have z equals t, and on the third page you have z equals z. Are they the same, or are they set different?
No. This one you want to have z equal to z. Because notice, if you like here, for this one, if I let like t equal pi over 2, I would get x is equal to 3 cosine pi over 2, y is equal to 3 sine pi over 2. So let's see, cosine pi over 2 is 0, so I'll get 0. Y is 3 times sine pi over 2, which is 3. But you've got to pick what z is. Maybe like z is 5. So the point that you're getting is 0, 3, and 5. So when you plot that point, You go in the x direction 0, in the y direction 3, and then up 5. 1, 2, 3, 4, 5. You notice what's happening here with this parametric representation here. You're plotting your point along the circle in the xy plane, and then z equal, you're saying let z be whatever you choose it to be. That will give you your height, how far above you are the xy plane or below. Okay? Notice this is a curve. Everything is in terms of t. You have one parameter because it's a one-dimensional figure. It's sort of like a line. This curve is two-dimensional, and it has two parameters, t and z. Now, sometimes you go, oh, representing a surface parametrically is really difficult. It doesn't have to be difficult. Here, they have an equation of a plane, and they're asking me to represent it parametrically. And as we said, when you have a surface and you represent it parametrically, you need two parameters. So look at this. I'm going to let x just be x. And I'm going to let y just be y. And therefore, z, if I solve that top equation for z, z is 6 minus 2x minus 3y. Okay? Now we could write this parametric representation using vectors. My position vector, r of xy, is normally xi plus yj plus zk. But in this particular case, x is x, so it would be xi. Y is y, which is yj. And z is 6 minus 2x minus 3yk. Okay? Notice, if you let x and y range over all the numbers from minus infinity to infinity, you would get all the points that are on the plane. Okay? And don't be disheartened about this, because think about this. If you graphed this plane, I wanted to graph this plane. If I let y and z be 0, I get x is 3. So it's crossing the x-axis at 3. If I let x and z be 0, I get y is 2. It's crossing the y-axis at 2. And it's crossing the z-axis at 6. It looks something like this. Now you guys know, though, that it goes forever. You know, a plane doesn't have edges like this. I'm just showing part of it. But now you think, if you pick a point in the xy plane, and I'm going to pick one in this little triangle so I can see it, you pick your x and your y coordinate, maybe like 1, 1. As you go up, the z coordinate is determined, right? If you pick your x and your y coordinates, the z coordinate is determined by what you chose that x and y coordinate to be. Okay, so we have like 2 degrees of freedom when you represent a surface parametrically. And right now you're thinking, why would you want to do with it? But we'll see in a few minutes there's lots of things that we can do with it. A plane we can also think about a plane in terms of vectors. Let me show you the following. Suppose, and I don't really like this picture, so let me redraw it a little bit. For me to show you a plane in three-dimensional space, what I need to do is, first of all, show you one particular point that's in the plane. I'm going to call that P0. All right? Now, the vector R0 is the position vector pointing me to that point. It says that point's on the plane. So I got this point that's just suspended in three-dimensional space. Now, if you tell me 2 vectors that are parallel to the plane, maybe my plane has this vector, and maybe it has this vector parallel to the plane. Do you see that those 2 vectors are sort of like the point shows you where you got to go to start? You with me? And then your vectors are like your framework that you can lay your plane down upon. You with me? Like in three-dimensional space, here's your point. Here's my point, which is my tip of my finger. Maybe you might have one vector going this way, and then I have another vector going this way. Your plane's going to lay right on that. Now, how are you going to represent points that are in the plane? Well, let's look at a picture like I have here. Think of this as, you got your x, your y, and your z. I need R0 showing me how to get to my starting point. That's vector R0, the position vector to the initial point. But now, since this is my framework, we're saying you can stretch A any amount, stretch B any amount, draw how much you stretched B by, Because remember, when you add two vectors, you draw the first one, and then you draw the second one where the first one ends. And this is a point that's on that plane. Now, how do we get to that point? You add this vector plus this vector plus that vector to get that point on that plane. Now, notice we could, to get this vector A stretched this much, we say multiply it by some number to stretch it to get this amount. And multiply vector B by this much to get to this point. And the position vector pointing me to this point that's in the plane, which I'll call R, is equal to the first vector plus the second vector stretched by so much and the third vector stretched. And this will give me a parametric representation of the plane. Are you with me? Notice, just to go back through it, do it one more time. If you've got your vector, you have an initial point, which we will call P naught. Then we have two vectors. We're saying, okay, this is your framework, A, and let's say B. A and B. Now, your plane is laying on that. But we could stretch vector A by some amount, which we're going to call UA, U some number. And we're going to stretch vector B by some amount, which we will call VB. This is vector R naught, which is the position vector, which is just taking you to the initial point. If we take, remember when you add vectors, you draw the first one, you draw the second one where the first one ends, you draw the third one where the second one ends, and my resultant starts where the first one starts and ends where the second one ends. This is vector R, which is the initial point plus the first vector stretched by a certain amount plus the second vector stretched by a certain amount. And this can give me a parametric representation of my plane. Now notice this U and this V, those are my parameters. A, B, and R naught are all going to be fixed vectors. So let's look at this guy right here. You go, what does this have to do with what she was just doing? Notice I say identify the surface. Now notice I'm going to rewrite this R as my constants are 3, 2, negative 1. So it's the vector 3, 2, negative 1. Write it as a vector. Plus, now we've got u's, right? We've got a u times 1, a u times a negative 1, and a u times a 1. Plus some v times, this is v times a negative 1, v times a 3, and v times a negative 2. Do we all see that I could rewrite this as this? Because it's 3i plus u times I plus v times a negative 1 times I. So the I part's 3 plus u minus v. The j part, that's here's 2j minus 1u times j plus 3v times j. And this is v. Notice we have v's here, here, and here. So it's v in the x component is going to be times a negative 1. In the y component, it's going to be times 3. And in the z component, it's times a negative 2. So notice this right here is the point on the plane. We have a point on the plane that's 3, 2, negative 1. That's my starting point. And then two vectors parallel to the plane are 1, negative 1, 1, and negative 1, 3, negative 2. So this is the parametric representation of a plane. Where one point, now notice if you let u be 0, if you let u be 0 and v be 0, notice, let's just look here. If you looked at what's r of 0, 0, notice if you put a 0 in for u, a 0 in for v, look what you get. 3i plus 2 minus 0 plus 0, 2j, plus negative 1 plus 0 minus 0, minus 1k. That's a point that's on the surface? Yeah, it's the point 3, 2, negative 1. And then you can let u and v vary from minus infinity to infinity, and you'll be getting all the points on the plane as it's sweeping out here, as we just showed. Okay? All right, determine a parametric representation of the plane through the point negative 1, 2, 3 that contains the vectors I plus j minus 2k and r minus 2j plus 3k. Well, we said that the parametric representation of our plane is equal to your initial point plus u times the one vector plus v times the other vector. All right, so r naught, that's the position vector pointing to you at your point. That's the point -1, 2, 3. Plus u times vector A, I'll call this vector A, it has components 1, 1, minus 2. Plus v, this vector has components 1, -2, 3. That's a comma there, okay? So it's your initial point plus u times your first vector plus v times your second vector. Now notice, if we wanted to, we could write this as a -1, 2, 3, plus you could multiply the u distributively. U times 1 is u times 1 is u times -2 is -2u, plus v times 1 is v, minus 2v, 3v. And we could combine similar terms, so we have it all. I'm going to combine the x components. X, x, x. So we have a -1 plus u plus v, comma, 3, excuse me, that's a 2. 2 plus u minus 2v, and the z component is 3 minus 2u plus 3v. And we have a vector representation of our plane. Notice, if you wanted to write it in terms of I, j's, and k's, this is your I part, plus your j part is 2 plus u minus 2v, and your k part is 3 minus 2u plus 3v. And it's a different way to represent a plane. If I looked at that parametric representation, I said, oh, what's a point on the plane? Oh, if I let u and v be 0, I get x coordinates -1, y coordinates 2, z coordinates 3. Okay, and you could let u be 0 and v be 1, u be 2 and v be 3, and just all the different combinations will generate all the points that are on that plane. All right, identify and sketch the surface with vector equations r of uv equals 2 cosine u I plus vj plus 2 sine u k. Now, just to help you think, what's going on here, my x coordinate is the coefficient of the I. So it's x is equal to 2 cosine u. My y is equal to this coefficient, v. And my z is equal to 2 sine u. Okay. Now, can you guys tell me, look at that. If I have x is 2 cosine u, y is v, and z is 2 sine u, any suggestions on what we can do with that? What do you think? They want me to identify and sketch this surface. Right now, you guys don't have a whole lot. You might have a little bit of intuition by recognizing what the form of a plane looks like parametrically, all right? But in terms of cylinders and hyperboloids, I don't think you really can picture that at this point, right? So we're going to look at this and say, could we rewrite this in terms of x, y's, and z's? And then maybe we can represent what it looks like. Because it says identify and sketch the surface. I mean, we could, pick in different values for u and v and look to see what it looks like, but no. We're going to try to tie it to something that we knew from before. Well, I see a cosine and a sine, people. What do you know about cosine and sine? Cosine squared plus sine squared is? Aha! So let's try x squared plus z squared. So that's going to equal x is 2 cosine u, and z is 2 sine u. So I have x squared plus z squared is 4 cosine squared u plus 4 sine squared u. I could factor out the 4, and I get 4 times 1, which is 4. So my x and z coordinates satisfy the equation x squared plus z squared is 4. And notice y is v. So y has nothing to do with what u is. You can just pick v to be anything. Well, what does that look like?
Cylinder.
It looks like a cylinder. Now, that's a cylinder that you're going to draw in the xz plane. So first you're going to draw your circle in the xz plane of radius 2. And since there's no y, you're going to drag it along. and drag it. And notice, as you pick what u is, you're going to be determining your x and your z in the xz plane, and then y is equal to whatever v is. That's how much you're going to be coming along, out along here, parallel to the y-axis, how far you're going to draw to get to plot your point. Okay, so what does it look like? It looks like a cylinder. Okay, and we were able to sketch it. So if something's given parametrically, look to see if somehow you can consolidate to be able to get your equation in terms of x's and z's. Okay, find a parametric representation for the surface, the lower half of the ellipsoid, 2x squared plus 4y squared plus z squared equals 1. Any suggestions? How many parameters are there? 2. What does this ellipsoid look like? It looks like a football, right? But they want the lower half. So normally, when we draw an ellipsoid, you know, you drew the whole thing. But we just want the part that's down here. You with me? The bottom half of the football. So we want the bottom half. Well, normally, if we just wanted the bottom half, we would solve for z. And I'd get z squared is 1 minus 2x squared minus 4y squared, right? And since I want to solve for z, normally we go plus or minus the square root of 1 minus 2x squared minus 4y squared. But since it's the bottom half, it's going to be z equals negative because it's the bottom half. Well, look how easy this is. Why don't we, for our parametric representation for this surface, let x be x. I mean, you could let x be u if you wanted to, but I figure why not use x, right? Let y be y. And let z be square root of, minus the square root of, 1 minus 2x squared minus 4y squared. Okay? If you wanted to write this as a vector, you could say r of xy is equal to x times I, because that's your x coordinate. Your y coordinate is y times j plus minus, I should have said minus, but that's okay, 1 minus 2x squared minus 4y squared times k. And that's a parametric representation of your football. How about this one? We want to come up with a parametric representation of the part of the elliptic paraboloid that lies in front of the plane x equals 0. Notice if you solve this for x, you would have x equals 4 minus y squared minus 2z squared. If you let y and z be 0, notice x is 4. 1, 2, 3, 4. And then as if y and z are anything other than 0, okay, if y and z are anything other than 0, your x is going to be less, and your paraboloid is going to be going like this. But they want it in front of x equals 0, so they want it, you know, when it comes to the yz plane, we're going to cut it off. My picture really stinks, but you can get the idea. You're cutting it off there. This paraboloid's coming like that, but we cut it off when it gets to the yz plane. Well, quite simply, you guys tell me, how do you think we can represent this parametrically? I have x in terms of y and z. Since x is written in terms of y and z, and you're allowed 2 parameters, what do you think your 2 parameters should be? Y and z. So why don't we let y be y, z be z, and x is 4 minus y squared minus 2z squared. Now, since they're saying they want to have you in front of the plane x equals 0, if you're in the front, that means they want to have x positive, right? So we want to have 4 minus y squared minus 2z squared greater than 0, or you could add your y squared and add your 2z squared, and we could say, okay, this is my parametric representation, but we're going to stipulate that y squared plus 2z squared has to be less than 4. Because if that happens, then your x is greater than 0 and you're going to be to the right of that plane. But a lot of times, if you have an equation in terms of x, y, and z, see what variable you can solve for, and then your parameters is the other 2 variables. And it's that easy. Okay, let's try this one. The part of the plane that lies inside the cylinder, z equals x plus 3. With x squared plus y squared equal to 1. Now notice z equals x plus 3. If I just draw it in the xz plane, when x is 0, z is 3. And unfortunately, when x is negative 3, okay, so it's coming down like this. And so if I draw it here, it's going to be coming down like this. So it looks something like this, but it's going down. You know, it's going below. It's what your plane looks like. That's going below the xy plane. And then we have the part of the plane that lies inside the cylinder. Well, x squared plus y squared equals 1 is this little circle. And we're coming up like this. And we're talking about the part of the plane that's getting cut off by this little cylinder. Okay, so probably it looks something like it's going to be coming down. It's something like that. It's sort of hard to draw, but it's like some ellipse in three-dimensional space. And we want to represent that parametrically. Well, what are your thoughts? When you see x squared plus y squared equals 1, and I say to you, represent that parametrically. How are you going to represent that parametrically? X equals cosine t, y equals sine t? Sure. When you have a circle of radius r, we would use, right, in general, if you had x squared plus y squared equals r squared, instantly we should know to represent x as r cosine t, y as r sine t. And if you check it, x squared plus y squared will be r squared cosine squared plus r squared sine squared. Factor out the r squared, you'll have r squared times 1 or r squared, right? This is how we would represent a circle parametrically. So here, x squared plus y squared equals 1. I'm going to let x be cosine t. Y is going to be sine t. All right. And if x is cosine t and y is sine t, what does my z going to equal? Oh, but wait a second. Okay, let's keep, I'm making a mistake here, so we'll talk about it in a second. Z is going to be what? Z is going to be x plus 3, so x is cosine t plus 3. Now, what did I do wrong? I'm looking at that, and you guys might be doing this too on a test. I look at that, and I'm a little bit shocked and a little bit upset, because how many parameters do I have? 1. So I have represented a curve, not a surface. What curve have I represented? I've represented the curve that's the border. You with me? The part that's just along the edge, because x squared plus y squared equals 1 is the edge. This is representing this curve, which is what you get when the cylinder, just the cylinder, intersects the plane. Notice, we're not just taking the edge, we're taking the whole interior of that circle. So we're not going to represent the x and the y as cosine t and sine t, because in two-dimensional space, I want to have the entire interior of x squared plus y squared equals 1. You with me? So instead of so if you think about it, you can have all these little concentric circles. X squared plus y squared equals r squared. You with me? So let's let x equal r cosine t, y equal r sine t, where I'm going to let t range from 0 to 2 pi, and r is going to range from 0 to 1, because we can go from 0 to a distance of 1 away from the origin. And then, since z is equal to x plus 3, we'll represent z as x, which is r cosine t, plus 3. And if you look at that parametric representation, how many parameters do I have? 2. And a surface needs to have 2 parameters, or it's not a two-dimensional geometric entity. It's a curve instead of a surface. Okay? All right. Now, what is this good for? Why does anybody want to represent a surface parametrically? You guys did very well. I mean, you got through like 14 weeks of calculus 3 without parametric surfaces. Let's go back and see why this is so cool, what you can use it for. here's a surface, all right? And this surface I'm going to assume is given by r of uv. I have a parametric representation of it. And this point right here, that corresponds to r of u naught v naught. So it's a particular point in space. And what I want to do is I want to figure out, we want to figure out the surface area, but first of all, what I'd like to do is maybe find the equation of a tangent plane. We've done that before. Let's see if we can do it with the parametric representation. So I say, wait a second. If this point right here corresponds to u naught v naught, if I hold v constant, v is equal to a constant, I get this curve right along here. Okay? And if I take the partial of r with respect to u, remember r is a vector, so the partial of r with respect to u, that means we're letting u change but v is held constant, gives me this vector. Notice this vector is tangent to the surface. I could also hold u constant and take the partial of r with respect to u. She should have a v here. I missed that. Okay, I have to fix it. That should be the partial of r with respect to v, because v is allowed to change, but u is held constant. And we get another vector, tangent to the surface. Do you see that these two planes, these two vectors, sort of like give you a framework that you can lay your tangent plane on, right? My tangent plane is going to be laying right on them. But now to get the equation of a plane, as I recall, you had to have a vector a, b, c, and a point x naught, y naught, z naught. This was your point on the plane. This was your vector that was what? Your vector that was normal to the plane. And your equation turned out to be a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. That's how we got the equation of a plane, right? So I have the point. That's going to be x naught, y naught, z naught. How do I get the vector perpendicular to the plane? If I have two vectors, how can I get a vector perpendicular to both of them? Cross product. Absolutely. Absolutely. The cross product of those two vectors is going to give me a vector that's perpendicular to both of them, which will give me, if I evaluate it at u naught v naught, will give me a vector perpendicular to the surface, which is perpendicular to the tangent plane at that point. So if r is written as x in terms of u and v times I, plus y in terms of u and v times j, plus z in terms of u and v times k, the vector partial of r with respect to u, evaluated at u naught v naught, crossed with the partial of r with respect to v, evaluated at u naught v naught, is normal to the tangent plane at r of u naught v naught. It sounds like a lot, but it's not. So here, find the tangent plane to the surface with parametric equations x equals u squared, y equals v squared, and z equals u plus 2v at the point 1, 1, 3. To get the equation of a plane, you need the vector a, b, and c, and then you go a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. They've been so kind to give me the point 1, 1, 3. So I don't know what a is, but it's going to be x minus 1, plus I don't know what b is, but it's going to be y minus 1, and I don't know, I'll fill these in a minute, and I don't know what c is, but it's c minus 3 equals 0. We have to find the vector a, b, c. How are we going to do that? Well, first, let's write our equation of our surface as a vector. R is equal to x, which is u squared times I, plus y, which is v squared times j, plus z, which is u plus 2v times k. So what is the partial of r with respect to u? Well, the partial of u squared with respect to u is 2u. What's the partial of v squared with respect to u? 0. What's the partial of u plus 2v with respect to u? 1. The partial of r with respect to v, partial of u squared with respect to v is 0. Partial of v squared is 2v. And partial of u plus 2v with respect to v is 2. This gives me a vector, this gives me a vector. I want to take the vector, I want to find the vector that's perpendicular to both of them, so I need to do the cross product. So instead of writing it like this, we can write it as r sub u crossed r sub v is equal to, we go I, j, k across the top, then we do our components for partial of r with respect to u. It's 2u, 0, 1, and 0, 2v, 2. And this equals I times, eliminate row and column that's I in, 0 minus 2v, minus j times, eliminate row and column that j's in, 4u minus 0, plus k times, eliminate row and column that k is in, we get 4uv minus 0. Okay? All right, now the problem is, it's, don't be plugging this in because we got all these u's and v's plugging around. We got to find, to get the point 1, 1, 3, what do u and v have to be to generate that point? Well, first of all, we have 1 equals u squared. Since y is 1, 1 equals v squared. And since z is 3, we have z equals u plus 2v. Now notice, z is 3. That's a 3 equals u plus 2v. Since u squared is 1, what are the possibilities that u could be? Plus or minus 1. Let's try u equal to 1. Well, if I let u equal to 1 and v equal to 1, aha, plug it in here, 1 plus 2 times 1, yes, is 3. This is what we want. If you let u be negative 1 and v be 1, it's not going to work for this. Okay? So to get the point 1, 1, 3, we need u to be 1, v to be 1. So our vector a, b, c that's perpendicular to the tangent plane is going to be ru cross rv evaluated at u equals 1, v equals 1. So the x component is going to be a negative 2 times 1, which is a negative 2. The y component is minus 4 times 1, which is a negative 4. And the z component is 4 times 1, which is 4. So that's my vector perpendicular to the plane. So you have to do a little bit of work to find out what your parameters are to get that point. So finally, my equation is my a was negative 2, my b was negative 4, and my c was 4. So I have a negative 2 times x minus 1, minus 4 times y minus 1, plus 4 times z minus 3 equals 0. And that's absolutely fine. You can leave it like that. I know you people can do a little bit of algebra. If you want to simplify it, you'd end up with x plus 2y minus 2z equals a negative 3. That's also okay, but this is fine. You know, I'm multiplying it out. If you multiply that out, negative 2x plus 2 minus 4y plus 4 plus 4z minus 12, and simplify it, you would get that. Say this again. I multiply through by a negative to get rid of the minus signs. Here, I can do it. I would do this. I would go minus 2x plus 2, minus 4y, negative 4 is plus 4, plus 4z minus 12 is 0. So I have a minus 2x minus 4y plus 4z. Let's see, 2 and 4 is 6. Minus 12 is a negative 6 equals 0. So I have minus 2x minus 4y plus 4z equals 6. And if I decide I don't want the leading coefficient to be negative, let's divide through by a negative 2. And we could end up with x plus 2y minus 2z equals a negative 3. And that's prettier than what I had before. Okay, let's do some more. Now, so parametrically, what have we done so far? Ru cross Rv is perpendicular to the tangent plane. But let's, before we go on, look what I was going to do in a second. If you have two vectors A and B, here's vector A. Let's let him be vector B. Here's vector A. Yes, when I take A cross B, I get a vector that's perpendicular to both of them. The reason I redid that is right-hand rule. Remember your right-hand rule, you go from A to B and your thumb's pointing in the direction that A cross B is. What is the magnitude of A cross B equivalent to? Remember, if you drew this parallelogram, drawing this parallel to this and that parallel to that, the area of the parallelogram determined by vectors A and B, drawn tail to tail, its area is equal to the magnitude of A cross B. Remember, we proved that. That area is equal to the magnitude of A cross B. All right, now, notice when you have a surface here, well, in fact, we have it right here. Notice the partial of r with respect to u is just giving you a vector that's tangent to this curve. All right, but in reality, if I take the but notice these little lines here are, see, I gotta fix this too. She should have a V here. To fix those two when I go back. All right, now notice here V is held constant, so we're letting u change. But notice each of these little amounts you can think of is u's allowed to change by a certain amount, delta u. And when I go from here to here, r changes by what we call delta r. And your delta r, how much r changes from here to here, would equal your partial of r with respect to u times your delta u. Because remember, along this curve, v is not changing. V is equal to a constant. So this little vector going from here to here could be represented as the partial of r with respect to u times delta u. Similarly, this vector right here could be represented as the partial of r with respect to v times delta v. And this little surface area would be the magnitude of partial of r with respect to u, delta u, cross with partial of r with respect to v, delta v. Now, these guys right here, they're scalars. They're just numbers. So we can factor them out. And what are we going to do? To find out the area, we're going to add up all those little areas, right? And as we let little delta u's and delta v's go to 0, this is going to go to the integral of the magnitude of ru cross rv. I'm going to write it as dA, or we could write it as du dv. Okay? So when my surface is given parametrically, if I want to get the surface area, each of those little rectangles, I could represent its area as being like that. And so therefore, my total surface area would be sum them all up, and I end up with this. This is easy to apply. When you're before we did surface area, but every single time I really picked it so that it was like z was in terms of x and y. What if you have y in terms of x and z? Or x in terms of y and z? Or what if you don't even have an x, y, or z? You got it in terms of u's and v's or thetas and phis. All right? How would I find my surface area? By using this. Now notice what you do. Get your surface done parametrically, and then all you have to do is figure out what the partial of r is with respect to u, partial of r with respect to v. Now what do these lines mean? Magnitude. Remember, the magnitude of a vector a, b, c is square root of a squared plus b squared plus c squared, right? You got to take the square root of, okay. And this dA is, this d is over what domain are your parameters ranging over to get your surface? What are your parameters ranging from? So let's do a few. All right, let's find the area of the surface of the part of the plane with vector equation r of uv equals 1 plus v, comma, u minus 2v, comma, 3 minus 5u plus v. And they're being very nice. They're telling me u ranges from 0 to 1, and v is ranging from 0 to 1. Okay, we're doing all right? Okay, so what is ru? It's the partial of r with respect to u. So I look at my x component, my y component, my z component. What's the partial of 1 plus v with respect to u? 0. What's the partial of u minus 2v with respect to u? 1. What's the partial of 3 minus 5u plus 5 plus v with respect to u? minus 5. Okay, now we've got to do the partial of r with respect to v. That with respect to v is 1. That with respect to v is negative 2. That with respect to v is 1. Okay, now our formula says we're integrating over the magnitude of those partials crossed. All right, so now we got to do a cross product. We got to figure out what is RU cross RV. That's I, J, K, 0, 1, negative 5, 1, negative 2, 1. Now wait a minute, I shouldn't say magnitude because right now I'm just doing RU cross RV. I'm getting the vector, not the magnitude. So this equals I times, eliminate row and column that I is in, so I have 1, all right, 1 minus 10, minus j times, eliminate row and column that j is in, 0 minus a minus 5, that's plus 5, plus k, eliminate row and column that k is in, 0 minus 1. So RU cross RV is equal to minus 9i minus 5j minus k. So the magnitude of RU cross RV is the square root of negative 9 squared, which is 81, plus negative 5 squared, which is 25, plus k squared, which is 1. So this is equal to square root of, I think it's 107. Now we're not finished yet. The formula for area is the magnitude over the domain that the u's and v's are ranging of. Now we just figured out the magnitude of RU cross RV is just square root of 107. My parameters are u and v, so that's my dA. Go back to the original problem. This is easy. What's u ranging from? From 0 to 1. What's v ranging from? From 0 to 1. People, we could write this as square root of 1 over 7, integral from 0 to 1, integral from 0 to 1 du dv. You're more than welcome to finish that, but this is just it. This is your u and this is your v. U is ranging from 0 to 1, v is ranging from 0 to 1. We're just finding the area of that square, so that's going to turn out to be a 1. If you don't believe me, you can finish that integration. Okay? Any questions? All right, so over and over and over for the next few minutes, we're going to be practicing how to do this. What's going to make it hard? Sometimes they're not going to give me the surface parametrically. I'm going to have to come up with a parametric representation. Okay, here's one. They didn't give me the parametric representation, did they? They said the part of the surface z equals xy that lies within the cylinder x squared plus y squared is equal to 1. All right, now notice what's happening here. X squared plus y squared equals 1 is a circle, right? But we're within that circle. Okay, so my xy, if I want to draw it in two-dimensional space, my xy is everything inside this little circle of radius 1. But first of all, what am I finding the surface area of? I'm finding the surface area of this. So I have to represent that surface parametrically. Well, shoot, they have z in terms of x and y, so why don't we let x be x, y be y, and z be xy. If they have it z in terms of x and y, go for it that way. So my r, notice, is a function of x and y, not u and v. And that is equal to x times I plus y times j plus xy times k, because z is k. So in using this formula here, we're not going to write RU cross RV. We're going to use RX cross RY, right? So what's my partial of r with respect to x? Well, let's see. Partial of x with respect to x is 1i plus 0j, and the partial of xy with respect to x is y times k. And ry is going to be 0i plus 1j plus partial of xy with respect to y is xk. So if I want to figure out rx cross ry, ijk, 1, 0, y. 0, 1, x. And that's going to give me I times, eliminate row and column that's i's in, 0 minus y. Minus j times, eliminate row and column that j's in, x minus 0. Plus k times, let's see, 1 minus 0 is 1. So we have minus y I minus x j plus 1. So what is the magnitude of Rx cross Ry? It's going to be the square root of y squared plus x squared plus 1. Now we're integrating the magnitude of Rx cross Ry dA. So we're integrating over square root of y squared plus x squared plus 1. We could write it as dx dy or dy dx over what's our region? What's our region? It's, remember, it was the stuff within the cylinder, x squared plus y squared equals 1. It's the interior of that circle. That's my base. That's what I'm integrating over. Good mathematician's a lazy mathematician. That looks like a circular region to me, so what kind of coordinates do you think we should use? Polar. I think we're going to use polar, huh? As we're integrating over the circle, x squared plus y squared equals 1. Right? That's a radius of 1. So I know that x squared plus y squared is r squared, right? So that's going to be the integral of 1 plus r squared. And what do I replace dx dy with? R, it sounds like hardy-har. R d theta. And what's r ranging from? 0 to 1. And theta is ranging from? Do you all see this is a nice simple u substitution? U is going to be 1 plus r squared. The du is 2r dr. You'll have to put a 2 in there. You with me? I don't want to. You can finish that. It's not hard. We've done these a million times. You'll get 2 pi over 3 times 2 radical 2 minus 1, which I did post for you. Okay, so I want to set these up. There is one that I'll talk about how you would do the integration. That's a little bit messy, but I think that one's worth going on. Okay, let's look at this one. We want to set it up. The part of the paraboloid, this is what we want to find the surface of, that lies inside the cylinder y squared plus z squared equals 9. So you have this paraboloid, and then we're taking the part that's inside y squared plus z squared equals 1. So since we have the surface that we're going to be integrating is in the yz plane, and that's y squared plus z squared equals 9, that's the interior of a circle whose radius is 3. So we want to represent my surface parametrically in terms of y and z. So why don't we let x be y squared plus z squared, and then y will be y, and z will be z. If you want to picture what this thing looks like, x equals y squared plus z squared is a paraboloid that's coming around like this. But y squared plus z squared equals 9. You're going to come through and you're taking the part, just the part that's inside there. That's the part that's inside that gets cut. You don't even have to really picture it, though. We could just let the mathematics take care of it for us. So first of all, let's write our surface, which we have parametrically as a vector. So r is y squared plus z squared times I plus y times j plus z times k. So we're going to take the partial of r with respect to y and get 2yi plus 1j plus 0k. And we're going to take the partial of r with respect to z and get 2zi plus 0j plus 1k. And we've got to figure out what is ry cross rz. That gives me I, j, k, 2y, 1, 0, 2z, 0, 1. This gives me I times, and it's 1 minus 0, so it's 1, minus j times 2y minus 2z is 2y, plus k times 0 minus 2z. So it looks like, let's see, we have r, partial of r with respect to y, partial of r with respect to z, is the vector I minus 2yj minus 2zk. So what's the magnitude of that? It's going to be what? Square root x component squared plus y component squared plus z component squared. So we're going to integrate square root of 1 plus 4y squared plus 4z squared. And we have to say over what region? Well, remember, it was over the region y squared plus z squared equals 9. This region right here, the interior of a circle. The interior of a circle whose center was the origin and whose radius was 3. Well, if I'm integrating over a circle, I'm going to be using polars big time. Notice this is in terms of y and z's. So we would let y be r cosine theta, z be r sine theta, but shoot, y squared plus z squared is r squared. So this is equal to the double integral square root of, notice you can write this as 1 plus 4 parentheses y squared plus z squared dA, which I'm going to get this as square root of 1 plus 4r squared, and for dA we'll put in r dr d theta. What's r ranging from? 0 to 3, 0 to 2 pi. And again, this is a simple u substitution. You've seen me do this 25 times this semester. I don't think I have to torture you again. So you're more than welcome to practice. You should get pi over 6 times 37 root 37 minus 1. Okay, but we're not going to do it. Okay, let's do another one. Setting them up, that process is, I think, and if you're at home, you're welcome to, just stop me and, see if you can do the next example. Now, as I recall, we did surface area before, right? We did it with z equals f of x, y. You had surface area on the last test. So you might be wondering, gee, I wonder if that formula that we memorized before, or that we put on our cheat sheet, and I'll just remind you what the formula was. If you had your surface is in the form of z equals f of x, y, and you had your, I draw my picture here, the surface is like here, and its shadow in the xy plane is, I'll call d. If you want to go back and look at your notes, because I'm sure most of you have cleaned that out of your brain, the formula for the surface area was the double integral of 1 plus fx squared plus fy squared dx dy, where x was the shadow of the surface on the xy plane. That's the formula that we memorized for surface area. So the question is, this process that we've learned with parametric equations, is it equivalent? Well, it better be. So let's just look for a second. Notice, if you have your equation as given as z equals f of x, y, you could represent this surface parametrically as x is x, y is y, and z is f of x, y, right? So your r would be xi plus yj plus f of x, yk, right? All right, now, if this is what r is, rx, partial with respect to x is 1, partial of that with respect to x is 0, and that's the partial of f with respect to x. Differentiate with respect to y, you're going to get 0, 1, and partial of f with respect to y. Do that determinant, you're going to get this. Take the magnitude, and you'll get the square root of that squared, which is the partial of f with respect to x squared. That's the partial of f with respect to y squared, and that's 1. And what's my x and y ranging from? That would be my shadow, which would be my region D. I like this process because I forget this formula. But with the parametrics doing that process, I can remember how to do it. So I like now either way's fine. Either way's fine. If you love this, you're more than welcome to use this if you can write your surface in terms of z equals f of x, y. What if instead it's x is in terms of y and z? Then I think I'd go back and do it the other way and write it parametrically. So in this one, find the area of the paraboloid z equals x squared plus y squared that lies under the plane z equals 9. Now if you notice, this paraboloid looks like this. Okay, and this is the surface that we have right here. All right, so if we wanted to use the formula, if we take the image of this surface, where are we? We're down here, right? it's the circle x squared plus y squared equals 9, which is its thing. So we're going to go, let's see, what's the partial of f with respect to x? It's 2x. What's the partial of f with respect to y? It's 2y. So we'd be integrating 1 plus fx squared plus fy squared dA, which would give us square root of 1 plus 4x squared plus 4y squared dx dy. Again, this looks like it's a circle, so why not use polars? So I'll replace x squared plus y squared with r squared. R dr d theta, what's r ranging from? 0 to 3, and 0 to 2 pi, and you'll get the answer that I have printed there. Okay, so you can do it that way. I like the parametrics, but sometimes, I mean, this does work. I mean, that's what we did last chapter, so, you know, if you have it in z in terms of fxy, why not go ahead and do that? Okay, one more. Yeah, this is the last one. I wanted to mention this one because the integration in this one is not so nice, so I just want to talk about it for just a minute. Find the area of the surface y equals 4x plus z squared that lies between the planes x equals 0, x equals 1, z equals 0, and z equals 1. Well, the region that you're integrating over is from x equals 0 to x equals 1, and z equals 0 to z equals 1. So you're integrating over this square. You're integrating over that square. So setting it up is pretty straightforward. We'll do that quite quickly. Since y, the surface, has y in terms of x and z, I think we'll let x be x, y will be 4x plus z squared, and z be z. We'll let our r equal xi plus 4x plus z squared j plus z times k. So the partial of r with respect to x is 1i plus 4j plus 0k. And the partial of r with respect to with respect to z is 0i plus 2zj plus 1k. To save time, I've already done the cross product, because I know you're getting sort of tired of listening to me. If you want to stop the tape and see if you get the same answer, fine. But you'll get 4i minus j plus 2zk. All right. And so the magnitude of rx crossed rz is square root of 16 plus negative 1 squared is 1 plus 2z squared is 2z squared. All right. So we are integrating square root of 17 plus 4z squared. We could write it as dx dz or dz dx. Now let's do it dz dx. As z is ranging from 0 to 1 and x is ranging from 0 to 1. Now, this particular integration I could do with a trigonometric substitution. That's fine. And when you do the trigonometric substitution, you're going to get a secant cubed. And with the secant cubed, you've got to break it down into parts, letting your u equal secant and your dv be secant squared. All right, which means that, I mean, it's just a horrendous integration to do. I have no problem if you get an integration like this, if you open up your textbook and look in the back of the book, and it is fine if you can find an integration table that applies, that's in the form that you want. Now, you really can't see what I'm printing right here, but looking here, they have an integration. Let me just write it. They say that, this is number 21 on page 6 of the integration tables, and they tell me the integral of the square root of a squared plus u squared du is u over 2 square root of a squared plus u squared plus a squared over 2 log of u plus square root of a squared plus u squared. Okay, let's see if I have it copied right, because there's a lot there. That is a u, right? Okay, u plus square root of a squared plus u squared. Now, looking at what we have here, looking at this inner integral here, okay, notice it's in that form I can let my a squared be 17. But the problem is I have a 4z squared here. I don't have a, I have that 4 there. So what I would do is I would write this as 17 plus 2z squared dz. I'm going to let 2z be u. So 2dz is du, or dz is 1/2 du. So this is going to become the integral from 0 to 1 of square root of 17 plus u squared, and for dz, I'll put in 1/2 du. Now notice your a squared is 17, or a is square root of 17. All right, so just using my integration tables now, that says this is equal to u over 2 square root of a squared, that's 17, plus u squared, plus a squared, that's 17, over 2 log of u plus square root of a squared, which is 17, plus u squared. Except I forgot one little thing. I have my 1/2 there. Okay, so this is going to equal u over 4 square root of 17 plus u squared, plus 17/4 log of u plus square root of 17 plus u squared. And, not forgetting, 2z is 2. 2z is u, not 2. I'm getting tongue-tied. So we can plug in 2z for u. And this gives me 2z over 4 square root of 17 plus 4z squared plus 17/4 log of 2z plus square root of 17 plus 4z squared. And we're going from z equals 0 to z equals 1, which gives me, putting in a 1 here, 2/4 is 1/2 square root of 17 plus 4 is 21, plus 17/4 natural log of 17, this is a 0, this is a 2, plus 17 plus 4 is square root of 21, minus, you pop a 0 in here, this is 0, and this is 17/4 log of 0 plus square root of 17. All right, which looks horrendous, but this is one big ugly number. And we're integrating that ugly number from, I come back and look, from 0 to 1. We can factor out the ugly number, and we just get x, because the integral of 1 dx is x. From 0 to 1 just gives me 1. So my answer is the ugly number, square root of 21 over 2, plus 17/4 natural log of 2 plus root 21, minus 17/4 log of root 17. And it's fine to use the integral tables. Like if you even have like an x sine x, parts are great, and I'm thrilled that you can do parts. If you have a 1 over 1 plus u squared du, that's fine. But if you're stuck, open the back of the integral tables and look to see if you can find one that you can use. For homework, what I would like you to do is read pages 1134 to 1142, and then on pages 1142 to 1144, let's do 1, 3, 17, 19, 23, 35 to 41, the odds. And think about it, we only have 3 more lectures in Calculus 3, and you will have completed the course. So see you next time. Bye-bye.